Hey everyone, welcome back. So today we're going to be solving another question in the DP series. It's called unique paths. Right? This is part of 2D DP, right? So let's get started. Okay. Now, so you have a so basically you have a grid, right? And then you have start to finish, right? Your task is to basically figure out the number of unique paths that a robot can take to reach the bottom right corner, right? Okay. So the number of unique paths the robot can take to reach from the top to bottom right corner. Okay. Now, and one more condition is that to return the positive numbers, bottom right corner, the robot can only move either down or right at any given point of time, right? So this is the robot, right? It can either move only this way, right, or only this way. It cannot move this way, nor can it move this way. Okay. Okay. Perfect. Now, okay, you need to figure out the unique path. Okay. Just one disclaimer: I'm not solved this question yet. If you see, I don't have any submissions as such. I did read the question before the video, but I'm gonna be trying to solve it on the video itself, right? So that you'll be able to, if I'm stuck at a point, you'll know, and you're here to watch that solution. And if I try to figure out, if I try to overcome that point where I was stuck, you'll be able to learn new things, and you'll know where you're going wrong. That is the whole point, and it's fun for me as well to do it on the video itself, right, instead of doing it before and explain it, right? Yeah, so let's get started, right? So basically, let's take right, let's take a grid. Okay, basically what you're supposed to do is you have certain values in the grid, right? Okay. So this is marked as 0, 1, 2, and then 0, 1, 2, 3. Right? Are you given a square matrix? No, it's mn to n, so m and n can differ, right? So my task is to figure out the unique path that I can take to reach from. This is the this is my source, right? And then this is my target, right? So number of unique paths that I can take. Okay, let's actually visualize the solution, right? Let's see how many paths there is to take. Okay, if I can only, so one more thing is I can only move this direction, right? Or I can only move this direction, right? I cannot move any other direction, right? So yeah, given this constraint, we need to figure it out. Okay, let's try to figure it out. Okay, one path that I can take is I can move completely right and then completely down, right? So I have one path with me. Count. I have one with me, right? And the second path that I can take is I can move down, I can move right, right? So the count is 2, right? Or I can do one more thing is where I can move right, and then I can move down, and then I can move right, right? So count becomes 3, right? Another path is I can move right, I can move down, I can move right, count becomes 4, right? And another path is I can move down, I can move right, I can move down, right? So count becomes 5, right? Or I can move completely down, I can move right. Can I move up? No, I can't move up. That is false because you can only move right or down. So this path has already been covered, right? Or I can move like this, 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 right? Count becomes 6. Okay, so this keeps on going, right? You get the point, right? If you take a smaller example, if I just take this particular grid, and then I draw just one line, right? And then I take 0, 1, 0, 1, right? This is my source, this is my target. How many paths can I take? I can take this one, I can take this one. So 2 paths. So count is 2, right? Is there any other path that I can take? I can either take this path, right, or I can take this path, right? Or can I? Okay, I can't take any other path. Perfect. So with this, we need to figure out how can we find the total number of unique paths that I can take to reach the target. Right? So for this example, it is pretty simple, right? But for this one, if you see, there's so many different possibilities. It actually keeps on going, right? So yeah, so we need to figure it out. Okay. So okay, I think there are two approaches to this problem, right? First approach is top down, right? And the second approach is basically tabulated, or you can call it iterative. Right? I'm going to be generalizing the formula for top down because I'm comfortable with that. But so the thing is, the difference is iterative was also almost the same thing once you figure out top down. Once you figure out the generic formula, right? Your iterative is also the same thing. It's just that the base condition will change, right? But I'm gonna figure out top down, and iterative is simple. But in this problem, I'm gonna try to figure out top down. Okay. Now, by top down, what do I mean? Right? I have my source and I have my target, right? What am I gonna do? Instead of starting from the source, I'm gonna see how many paths are there to reach my target, right? From this point, what I'm gonna do is I'm gonna see how many points are there, how many paths are there, in how many ways of unique paths are there to reach this particular target, right? So with the given constraint saying that I can only move down or right, I have only two paths, right? I can either come from here or I can come from here, right? Is there any other path? No, right? There's no other path. I can either come from here or I can come from here. These two are the only paths. Perfect. Okay. Now, we have broken down our problem. Why am I saying that? Now that we figured out there's only two paths, that is either this or this, right? Now our problem became a bit smaller. Why? Because now our target became this particular point or this particular point. Okay. Now let's see how many ways are there to reach this particular target. This particular target. Right? How many ways are there to reach this target? Again, with the given constraint, you can only come from this particular grid or this particular grid, right? These two are the only ways that you can, right. So perfect. So these two are the only paths that I can take to reach this particular point. Perfect. Now let us go to this point a bit later, right? Let's go to this point a bit later, right? Let's come to this particular point. Okay, how many ways are that? Now our target became even smaller. What are we trying to do? We're trying to break a bigger problem into smaller and smaller problem until we reach a base condition, right? That is what I'm trying to do. Now I have so this became my new target, right? This became my new target. Okay, how many ways are there to reach this particular target? How many ways are there? I can either come from here or I can come from here, right? But coming from here would be invalid because this is out of the grid. Okay, so my only option to reach this target is coming from this particular way, right? Perfect. Now this is my only way. Okay, now this became my new target. Okay, this became my new target. Or what I think is we can do something a bit different, right? How many ways are there to reach this particular point? See, when we were doing for this one, we had two different ways, right? You can either come from here or come from here. But if you consider only this particular point, we have only one way. right? We have only this way to come, right? Is there any other way to come? No, there's no other way to come, right? We have only this way to come. And since the question is asking us to return the number of ways, and I am saying that there's only one way to reach this particular target, can I say that when it reaches the row 0, there's only one way to reach any point in that row 0? Let's think about it again, right? What am I saying? I've reached the 0th row, right? In the 0th row, I'm saying that there's only one way to reach this 0th row, right? It's only from here. From source, I can go here, then I can go here and reach the source, the target, right? There's no other way. So what I am saying is, since the question is asking us to return the number of ways that you can reach the target, right? Number of ways. What I'm saying is, for the 0th row, for any grid, any box in the grid, there's only one way to reach them, right? So what I can see is, I can make my base condition in such a way that if my row equals to 0, right? If my row equals to 0, what am I going to do? I'm going to say that return 1. Because why? Because there's only one way to reach the target. Perfect. Okay, done. Now this is done. Let us come to this particular target, right? Let's come to this particular target. How many ways are there to reach this particular target, right? Let's look at it. How many ways are there to reach this particular target? I have two ways, this one or this one, right? Again, it becomes my sub problem, right? This becomes a target and this becomes a target. Similarly for this one, what is it? It's either this way or this way, right? So if you see, my target reduces now again. This becomes my target, this becomes my target, right? For this one, what is it? It's either this way or this way, right? Again, the same thing. This becomes my target and this is already my target. Okay, so okay, now let's forget about these points. Let's come to this particular target. Okay, now how many ways are there to reach this particular target, considering you only move right or down? It is the same as a 0th row, isn't it? The same as 0th row, right? From source, if you want to reach this particular target, what do? You move down and reach it. Is there any other way to reach it? No, you cannot come left. Left is not possible, right? Left is not possible, so you cannot come like that. There's only way that is down. Okay, and since the question is asking us to return the number of ways, I can return only one. Okay, so what I'm going to do, I'm going to return 1. So same thing in this if condition, what I'm going to do is, or my column equals to 0, I'm just going to return. This is my base condition. Perfect, we achieve the base condition. Okay, now this is how recursively we will break the bigger problem to smaller and smaller problems, right? Now let's take a look into the recursive approach, right? What I'm saying is, ways of reaching. Okay, let's take a smaller example. Actually, let's take this particular example, or actually let's take an example from here itself. Okay, m is 3, n is 2, meaning row is 3 and column is 2, right? Row is 3, 1, 2, 3, column is 2, right? Okay, so 0, 1, 0, 1, 2, right? And if you see, this is my source. Okay, this is my source and this is my target, right? Okay, now let's figure out the number of ways, right? So this is ideally, let me mark the index as well so that it's easier for us, right? Let me mark the index. So this would be 0, 0, right? And then 0, 1, 1, 0, 1, 1, 2, 0, 2, 1. Perfect. Now we need to figure out the number of ways, right? Let me move this a bit bigger. Right? Figure out the number of ways. Okay. Now, what I'm going to be doing, I'm going to be starting from ways of reaching 2, 1. Right? So I have two ways of reaching. Either come from way of 1, 1, right? Or come from way of 2, 0. Okay? Now, this gets broken down into another problem. Way of reaching 1, 1 is way of reaching 1, 0, or way of reaching 0, 1. Right? Perfect. Now, if you see over here, we have hit our base condition. What is the base condition? Our base condition basically was, our base condition basically was this was a base condition. Now we have hit our base condition. If row is 0 or column is 0, we got to return 1, right? So here column is 0, here row is 0. So I'm going to return 1. I'm going to return 1, right? Since it's asking us to return all the unique path, we need to add it up, right? There is an instance of OR, right? I can reach the target from this place or from this place, right? So there's a sense of OR, right? So we're going to add it up. So what it's going to return, these two calls are going to return 2. So this is going to have 2. There are two ways to reach 1, 1. Let us look at it visually. Are there two ways to reach 1, 1? I can either come like this or I can come like this, right? Perfect. So it's correct. Right? Now this has reached, this is given back 2, right? Now 2, 0, right? 2, 0, since my column is 0, I'm going to return 1. So what this is going to return is 1, right? This will return back 1, this will return back 2, right? So 2 plus 1 is 3. Your final answer would be 3. Your final answer would be 3. Okay. Now let's see. Yes. Yeah, answer over here is also 3. Perfect. So our solution is correct. Okay. Let me code it up. Okay. Let me call it. Let me just keep it simple. Let me just call it ways. Okay. Int row and int top. Right? Our base condition has come to the base condition later. Let's try the recursive return, right? Ways of row minus 1 column, right? Or ways of row and column minus 1, right? Now here, if row equals to 0 or column equals to 0, I'm going to return 1, right? That's our base condition. Here what we're going to do is simply return ways of row would be m minus 1 and then n minus 1, right? Perfect. Now I think this should do, yeah, it's as simple as that. Let me run it. Oh shit, I didn't give a return type. It worked. Perfect, you got XYP. Okay, let me submit it now, right? If I submit this, will this work or not? Will I get any errors or will this go through? Let's see. I am saying that looking at the given constraint, it is going to give us an error. Let's see. Let me submit. It's going to give us a TLA. See, we got a TLE, right? Okay, let's see why we got a TLE. Okay, so you might ask me, Siddharth, this problem is related to DP, and you're talking about top-down approach, bottom-up approach, and all of that. But you never use DP over here. It's only recursion that you're doing, or you're doing backtracking, right? You never use DP over here. Okay. So you can ask me, how is it DP, and why are you not using DP? Right? You're exactly right. I'm not yet used DP over here. Right? What is DP? It's dynamic programming, and what do we do in DP? We store the already processed value and we use it someplace else so that it doesn't have to be processed again. Right? That is the whole point of DP. Right? Now let's look at it. Okay? Let's take a bigger example actually, right? To see why we're getting a TLE. Okay. Let us go with this itself. This particular example. Okay. Now, to reach this particular target, what I'm going to do, two ways of reaching 2, 3, I have two ways, right? Ways, I can come from 2, 2, or I can come from 1, 3. Here again it gets broken down. Way of reaching 2, 1, or way of reaching 1, 2. Here again it gets broken down. Way of reaching 2, 0, or way of reaching 1, 1. Right? Again this gets broken down. Way of reaching 0, 2, or way of reaching 1, 1. Right? This will return 1. Right? Way of reaching 1, 1 will get broken down into 0, 1, or way of reaching 1, 0. Right? 0, 2 will return something. Right? This will return something. Again, this will get broken down into way of reaching 0, 1, or way of reaching 1, 0. Right? Okay. After all of this is processed, since we hit a base condition, all of this is processed. Now I'll come down. Right? I'll come here. Way of reaching 1, 3 is way of reaching 0, 3, or way of reaching 1, 2. Right? Again, 1, 2 will get broken down into different parts. This will get broken down into different parts. This will get broken down into different parts. Right? Now it is written. Now tell me something. In each level of the recursive tree, how many calls are being made? If you see in the first one, 2 power 0 calls are being made. Second one, 2 power 1 is called, one number of calls is being made. Third one, 2 power 2. Fourth one, 2 power 3. It keeps on going until 2 power n. Right? Until 2 power n, as in until we reach 0. We're starting from n to 0. So until 2 power n, we're starting from n and we're reaching 0. So 2 power n calls will be made in the end. On the worst case, 2 power n calls will be made. Right? Not in the worst case. Actually, 2 power n calls will be made. On the worst case, for the worst test case, how many calls will be made? If you look at the constraint, there will be 2 power 100 calls will be made of the worst test case. 2 power 100 calls. That's a huge number. So of course you're gonna get a TLE. Okay. So this is where we need to think of a better approach. Our approach is 90% correct, right? The other 10% is a optimized approach. Right? Okay. Now, so when you're applying DP, you shouldn't just blindly apply DP, right? You need to know why it is being used, what is the purpose of it, and what does it solve. Okay. Now, what am I saying? If you look at this example, if you see in the left subtree, this is the left subtree, right? That I got, right? If you look at it in the left subtree, I have calculated the value of way of 1, 2. I've calculated the value of way of 1, 1, right? Now I've calculated it. Now I'm coming to the right subtree. when I'm coming to the right subtree, what am I doing? I'm coming to 1 comma 2 again, and then I'm calculating this whole thing again, right? I'm coming to 1 comma 1 again, and I'm calculating this whole thing again, right? I'm calculating this whole thing again. So this is being so this is being repeated, this is being repeated, right? This for a smaller case. If you look at a bigger one, there'll be a lot of recursive calls that are being repeated. Now what I'm saying is, okay, I'll store this particular result of this recursive call, right? For the in the first time when I make that call, I'll store it, right? I'll store the result of v of 1 comma 2 somewhere, right? The first time I calculate it, right? The next time I come to that, instead of processing this entire result again, making recursive calls again and again and again and again, I will use a stored value to return the answer, right? Since it's already stored, I know that that is the value I'm going to get for this as well, right? So I'm simply going to return it. So if you see, we're not going to make a recursive call again, right? It is all one operation to fetch the value and return it, right? So how big of a difference is it making, right? From 2 power n, we're getting it down to n. Why n? Because only on the left subtree you're calculating the fresh values, the values for the first time, you're storing it. On the left subtree it's going till 0, you're calculating the value and you're storing it, right? You're storing it, let's say somewhere, right? You're storing the value. When you come to the right subtree, this particular right subtree, you're never calculating it again. You're just returning the stored value, which is O of 1, right? So your time complexity would be for the left subtree to store all the values, and it goes from n to 0. So your time complexity will be n, right? So it has reduced. So our time complexity has gone from O of 2 power n to O of n. Perfect. Now the question, where can I store it, right? It's very simple, right? What do you have to do? You have to store base of 1 comma 2, right? You have to store base of 1 comma 2, and you have to store base of 1 comma 1, right? Can I not create a DP array? Can I not create an array? Let's call it DP, right? I'll create an array, a 2D array, right? Because I need to store values of reaching a particular block in a grid, right? Which has a row and a column. So I'll create a 2D array, right? And I'll initialize those values with -1. Again, why -1? Or wait, I can initialize the value with 0 as well. Why 0? Because if you see, in the whole problem, right, is there any scenario where the number of ways to reach a point is 0? No. There is no way that a given block has 0 ways to reach it, right? There's no way. So I can initialize my answer with 0 initially, right? So that if the value is not 0, which means that since there is some value stored in it, and I can just return that value. Okay, it's exactly what I'm going to do. So what I'll be doing is, I'll simply create out a 2D array called DP. DP equals to new int of m and n. Right? Perfect. I've initialized it. I will pass it as a param, and I'll receive it as a param over here. Right? Okay. What I'll do is, before it even gets inside, I'll just check if dp of row and column, if it's not equal to 0, which means that there is some answer stored in it. All I'll do is I'll return dp of row and column. Perfect, right? Now this is where we're returning it, right? We need to store it also, right? So we're going to store it over here. Perfect. I've stored it. Now let's run it. Okay, wait, I need to call it from here as well. Now let me run it. Okay, let me use this test case. Okay, now let me run it. Okay, I got an error. Oh, sorry, the two. third case also run. Right? Now let me submit. Perfect. All are passed. So if you look at the time complexity, it's m into n. Why m into n? Because it's a 2D, right? But ideally, it's a 2D, right? So it consists of m and n, right? So if it was a square matrix, it would ideally be n itself, I believe, right? Since it's not a 2D matrix, I have to iterate through the rows and columns at least once, right? But the before approach, it was O of 2 power m into n, right? Perfect. So this is our solution, and I hope you understood how we're doing it. I would suggest you to go through the problem again, try to trace it on your own, try to figure out the solution. Okay. Thank you so much for watching.